All right, so let's address a few questions I got via email first, and then we'll start going to the live stream, like actual questions that you'll type in. So one question I got was asking about how do I find KQ if I'm given all the other information. And this is kind of the type of problem I like to ask simply because it does kind of get you out of the habit of thinking that there's kind of like, the test is going to be like cookie cutter questions. If you look at the packets, the question is going to be exactly like this. And again, this also kind of boils into how you approach these types of problems. So let me share my desktop with you really quick. We'll go to one of the homework assignments. So what is the solubility product? KSP for cobalt hydroxide. And I'm going to write that up on my board really quick. Cobalt plus 3 and 3 hydroxide, Q. And what is the KSP if the equilibrium concentration of hydroxide is 1.48 times 10 to the negative 11 molar? So, as I mentioned in a previous live stream, as I mentioned a lot in the videos online, you cannot do these without an IC table, you cannot do this without an expression for Q, and you cannot do this without KQ. So if you're trying to solve these types of problems without using that methodology, you're not going to get the right answer. So the first thing you need is KQ equals Q. So KQ, the equilibrium constant in this case, is KSP. KSP is a special case where we're looking at what's called the solubility product. So KSP equals Q, and Q here is the concentration of cobalt times the concentration of hydroxide to the third power. Things we need at equilibrium, KQ equals Q, and we've got our expression for Q. The third thing we need is the IC table. So for our IC table, we've got initial, change, equilibrium, and I'm going to do the numerical equilibrium in red. So I've got cobalt hydroxide, cobalt plus 3, and hydroxide. Now, we are not given any initial concentration, so the assumption here is that the concentration is 0. Now, the thing about our cobalt hydroxide here is that it's a solid. It doesn't appear on our expression for Q, so actually we don't even need this column. We only need the things that are actually involved. Now, our change values are always for products. They're going to be positive changes. And they're always going to be the extended reaction X multiplied by whatever the reaction coefficient is. So in the case of cobalt, it's 1. In the case of hydroxide, it's 3. This row is just simply I plus C. So we get X and 3X. And we're given the equilibrium value here as 1.48 times 10 to the negative 11. So we now have enough information at this point to solve this problem. The trick here is identifying what you need to solve. And the problem is asking you to find KSP. So if it's asking you to find this, that means that you have to know these. You can't have one equation and two unknowns. There could be only one unknown in the equation. So here we're going to look at, we can take either row. So let's say we take this row, we put in the first E row. We get it's X times 3X to the third power, which is going to be 27 times X to the fourth power. Well, we know that these two rows are equal. The blue row equals the red row, so we get 3x equals 1.48 times 10 to the negative 11. So x here is, let's see here, that's 4.28. 4.93 times 10 to the negative 12. So we can just stick in our value for x and solve it. Another option is that we can use this relationship. 3x equals 1.48 10 to the negative 11, so x is 4.93 10 to the negative 12. We also know that x equals this row, so we get 4.93 times 10 to the negative 12. And we can stick both of these numbers directly in here. So either option is approachable. It doesn't matter what you do, but the point here is that the IC table, you can figure out the extended reaction because you are given an equilibrium constant. That's why we have the two E rows. One is an algebraic expression in terms of extensive reaction. The other is a number if we are given it or what we are looking for. And that's pretty much how all those problems are solved for finding KQ. Set up the expression for KSP or whatever equilibrium constant you're being asked to find. Fill in your IC table with as much information as you have. If you're given equilibrium concentrations, use those to find your extent of reaction. And then you can use either E row to solve for the K cube. Now, another question I was asked was concerning the homeworks concerning the G, H, T, and S. So I'm going to share my desktop with you really quick. And we'll start with the first question. I think it was asked for questions 1, 3, and 5, but I'll check that. But the first question here is, what is the temperature, 1 decimal point, if the delta G is 59.9, and all those numbers. So give me just a minute to erase my board. So to solve these types of problems, what we're going to use is the Gibbs relationship. Now, there is one common mistake I see on this, but we'll talk about what that mistake is in just a minute. But the relationship is that delta G equals delta H minus T delta S. So you're given delta G in this problem is 54.9. The delta H here is 74.3. Temperature is what we're being asked to solve, and the delta S is given to you as 57.2, but it's joules per mole Kelvin, and this is the common mistake I see. Delta S is rarely ever reported in kilojoules because of how small it is. So you need to divide this first by 1,000 to get you into joules per mole, or kilojoules per mole Kelvin. So when you solve this, you're going to get the temperature here is 74.3 minus 54.9 divided by 0.0572. Now, the other thing to keep in mind, if you look at the answer, and I'll bring you back up to the desktop again, it's asking you for the temperature in degrees C, and this is to make sure that you're paying attention to your answer. The delta S here is in Kelvin, not in Celsius. So whatever answer you end up getting, you need to subtract off 273, not 273.15, although the answer will accommodate that. You need to subtract off 273 to get the correct final answer. Now, give me a quick minute to look up what the other questions were. Number 3. So number 3 is another one that if you look at it, it's there to make sure you're paying attention to what you're writing down. So it's asking you what's the entropy change if you're given these values of dg, dh, t. Again, you'll notice that when you're working with delta G, you're in kilojoules per mole. It's not asking you for the answer in kilojoules, though. It's asking you for the answer in joules per mole Kelvin. So when you work this, you're probably going to get an answer less than 1, and you need to convert that to joules per mole Kelvin. As far as number 5, we can work that, but it's basically going to be the same approach. That you're just going to use that Gibbs relationship, delta G equals delta H minus T delta S, and just put in the numbers. But again, with the temperature and with the entropy change, the big thing here is keeping track of the units. Again, keep in mind that delta S is reported not on a kilojoule per mole basis. It's too small for that. It's reported on a joule per mole basis, so it has to be converted. Also keep in mind that when it's asking you for a delta S or it's asking you for T, it's not asking it for you, not asking for it in the units you would work with it in the equation for the Gibbs relationship. You would work with it for the delta S in joules per mole Kelvin, and with temperature, it's asking you to convert centigrade just to make sure you're on top of that. You recognize that the temperature there is in the equation is Kelvin, but typically what we're going to report it in is centigrade. So those are the questions I was emailed in advance. Are there any questions out there from anyone who's watching right now? So how to set up a portion of a Hess's law problem. All right. So let me bring up one of the Hess's law problems. Bring up a reasonable Hess's law problem. So for a Hess's law problem, there are two ways to approach this. One is to add and subtract. The other is to use Hess's law directly. I'm going to advocate you learn how to do the Hess's law directly because that's the more practical version. So what I'm going to do is I'm going to try to work it out here on Word. So Hess's law says that the products minus the reactants will give you the enthalpy change of the reaction. So as a first pass for solving it by Hess's law, what you're going to do is just write out the Hess's law expression. So we get the delta H of this reaction equals the twice the enthalpy CaO, and the reason being is that we finished with 2 CaO molecules, so that's the enthalpy we finish with, minus what we start with. So we have 2 calcium atoms and 1 oxygen molecule. And this is all going to equal minus 1270, the reaction we're given. For this reaction, the delta H is the enthalpy of CO2 plus the enthalpy of CaO minus the enthalpy of CaCO3. Again, this is going to equal whatever the reaction is, minus 178.3. For this reaction, we get that the delta H equals the enthalpy of CO2 minus the enthalpy of carbon plus the enthalpy of O2, and this is going to equal minus 393.5. For our last reaction, we get the enthalpy of this reaction, delta H, equals twice the enthalpy CaCO3 minus twice the enthalpy of Ca, calcium, plus the enthalpy of O2, plus twice the enthalpy of CO2. And I've got the answer key up here, so it's minus 1,627, but we'll talk about how to get to that. So this is your first step with your Hess's law solution, is that you just want to write out Hess's law for each one. It's the enthalpy of the products times the reaction coefficient, so the enthalpy of each product molecule times its coefficient, minus the enthalpy of the starting molecules times their coefficient. So we got 2 calciums up here, so there's going to be 2 calciums down here, and O2 down here, and O2 over here. The next step is to cancel out everything that is 0. So any diatomic gas here, oxygen, is going to be 0 because it doesn't take we don't gain or lose heat by making oxygen from oxygen at room temperature. So your diatomic gases disappear. And if you have any pure elements, so something like calcium, calcium is an element, it disappears. Carbon is an element, it disappears. Now, a common mistake is students just start crossing a whole bunch of stuff out. If you have a molecule composed of more than one element, so something like CaO, this is most certainly not 0. So you can't cross it out by default. And what this will leave you with is a series of algebraic relationships. And the way we solve it is, well, we've got enthalpy of CO2 here is minus 393.5, so we would just stick that in down here. So the enthalpy of CO2 is minus 393.5. If we want to figure out the enthalpy of CaCO3, well, we know that the enthalpy of CO2 is minus 393.5 from the third reaction. And the enthalpy of CaO from up here is minus 630. So we can rearrange this equation and this number that we produce here will be the number we stick in down here. So this is how you take the Hess's law approach. You write out Hess's law for each reaction, cancel out everything that's zero, and then just start kind of working through the algebra to figure out what the answer is. And this would be true if we switch down to the Gibbs equation down here. So if we go down to Gibbs, we have the same reaction. It's just got different values. Gibbs, instead of H, we're working with G, but we take the exact same approach. So KSP is always going to be done doing ice tables. We're not going to really work with finding KSP from thermodynamic values. So for this one it says, I'll show you the discussion, show the discussion board for people to see. The KSP of aluminum phosphate is 1.84 times 10 to the negative 12. What is the concentration of aluminum phosphate at equilibrium? What is the mass solubility of aluminum phosphate? And here you're going to discuss your strategies. So again, with all of these types of problems, you can't get away, you can't skip over an ice table. You have to use an icy table to solve these types of problems. Now, this also presupposes that you know what aluminum phosphate is. That's more of a chemistry 1 concept. So aluminum phosphate, Al3BO4, 2 solid. KSP, if you look in the notes, KSP is just simply taking a solid and dissociating it into its ions. So 3Al plus 3, 2 phosphate minus 2. And you're given that the KSP itself equals 9.84 times 10 to the negative 21. So to solve the first point, the 5 points, what's the concentration of aluminum phosphate at equilibrium? Again, you're going to need 3 things. KSP equals Q. And Q in this case is the concentration of aluminum to the third power times the concentration of phosphate to the second power. So you've got your expression for Q. You need your IC table. Now we can leave off the aluminum phosphate simply because it doesn't appear in our expression for Q. We have I, C, E, and red E are equilibrium values. You're not given any starting concentrations, so you're going to assume they're zero. If you're given a starting concentration, like you're going to see for the forum that's actually shows up after Tuesday, the one beneath it, if you're not given a value, assume it's 0. So for the aluminum, we have a 0 molar starting concentration. The change, extent of reaction, times the reaction coefficient, so 3 and 2. So at equilibrium, we have 3x and 2x. We're not given equilibrium values, but we are asked to find them. So these are what we're trying to solve for. So what you would do from here, plug in your expressions. You'd have 3x cubed times 2x squared. Solve for x. X is not the answer in this case. X is just going to get you to these numbers. So 3 times x is the concentration of aluminum. 2 times x is the concentration of phosphate. Now, X here is an extent of reaction, but when it asks you for the mass solubility, there is a simple shortcut. So your mass solubility is simply X times the molecular weight of the compound. So once you find X and multiply it by the weight of aluminum phosphate, that will give you the mass solubility. But generally, we're not going to find equilibrium from delta G unless you're asked to find it explicitly, simply because it's kind of, it presupposes you have the thermodynamic values on hand, and even then you would still want to go measure it anyway, just to be sure. More likely, if we're going to connect delta G to KQ and vice versa, it's just going to be asking you what's the relationship between the two, or just use that relationship, but not solving it for something like this. Okay, the next question I'm going to ask, what is KQ of delta G is 120 kilojoules per mole at 25 degrees C. So the relationship here, KQ equals E minus delta G0, or delta G0 over RT. Conversely, we can rearrange this. Delta G is minus RT ln KQ. R in this case, 0.008314. Temperature in this case needs to be Kelvin, so if you're given 25 degrees C, this is going to be 298 Kelvin. And from there, it's just kind of plug and chug. Yeah, however you want to present your report, I just need to see a presentation. So if you want to do a voiceover with like photos or PowerPoint, go for it. Are you putting the negative in there when you raise the exponential if you're getting such a tiny power? Because that's would be my thought is that you're getting, yeah, it should, oh, I'm sorry, misread your answer. Yeah, it's supposed to be 9.23 to the negative 22. So for that question, yeah, it's 9.23 to the 22. Oh, it looks like there's a typo in that. That should be a negative. I can fix that. Yeah, it should be negative 22. I just think there's a typo in this key. Yeah, it looks like there's supposed to be negatives on all those answers, because if that's a positive delta G, that should be a tiny KQ. And I'll try to get that correct in the next day or two. Yeah, you're welcome. So manipulating equilibrium constants and pressure dependence of reactions. So we'll talk about, unless you have a specific one you want to work on, we'll just go over the first problem in each one. So we'll start with manipulating equilibrium constants, and this is one we're not going to worry about worrying with numbers so much as understanding what the end result of manipulating these equilibrium constants are. This kind of starts showing up as you get to higher levels of chemistry. So the question is, if the following two reactions are added together, what happens? So let's talk about some general rules. And typically what I do in a seated classroom is I make you prove these rules, because I found that when students do this, when they're just told the rules, the rules aren't retained. So one thing to kind of help you out here is that the equilibrium constant always has to be positive. And because think about it, it's concentrations, and concentrations can't ever be negative. So if you multiply and divide, it's impossible to finish with a negative number. So if you have two positive numbers and you multiply them together or divide them, you always finish with a positive number. If you add and subtract them, you can definitely finish with a negative number. So off the bat, any answer you have for KQ being based off of other equilibrium constants is not going to involve addition and subtraction. It's always multiplication and division. So the rule is, when we add reactions, we multiply their equilibrium constants. When we subtract them, we divide them. When we multiply a reaction by a constant, we raise the equilibrium to that constant. So for the first one, it asks what happens if you add the two reactions. Well, there's a K1 and a K2. Saving that marker. If we add the reactions together, we're going to multiply the equilibrium constants. So this is where, I'll bring it up on the desktop, show you the desktop. This is how we get the K1 times K2. Now if we drop down to the last one, it says what would be the final expression for KQ twice the second reaction subtracted from the first. Well, if we're going to use twice this reaction, we're going to double K1, we're going to effectively square it. So by doubling this reaction, we square the equilibrium constant. Now this is where you can get the K1 squared is going to be a potential answer. Now, I'm sorry, it's second reaction, so we're going to have K2 squared. So we're going to have K2 squared in our final answer because we're taking twice the second reaction. If we're going to subtract, so this is what it's saying, is if the second reaction subtracted, we're going to divide by it. So we're going to divide by K2 squared, and we're subtracting it from the first reaction, so that's going to give us K1 divided by K2 squared. So that's how they work. If you're going to add them, multiply them, you're going to subtract them, you're going to divide them, and if you're going to do it more than once, so in this case you're going to subtract twice the reaction, you're going to raise the equilibrium constant to that value. Now, concerning the other one, the pressure dependence, there's actually a fast way to do this. So the pressure dependence is describing basically what happens to Q. So to figure this out, the pressure dependence is the number of gas products minus the number of gas reactants. And where this comes from is that concentration, which is what we have in our expression for Q, can be rewritten in the ideal gas law to be the mole fraction of I times P naught over RT. And this just comes from the ideal gas law, PV equals X in RT. So if we rearrange, hold on. There we go. That's from Galton's law. We rearrange to get molarity, which is moles per unit volume. We get Xi P naught over RT. So if we put this in our expression for Q, we'll end up getting the pressure of this P naught raised to a certain power. So if we go to the homework, and I'm bringing it up on the desktop, we have 1 mole of gas here, 1 mole of gas here, so that's 2. We have 1 mole of gas here, 1 mole of gas here, that's 2. So 2 minus 2 is 0, so we get a P0 dependence. For this one, we finish with 2 moles of gas, and we start with 1 plus 3 will give us 4, so 2 minus 4 gives us that -2 dependence. For this reaction, we have 0 moles of gas, and we have 1 mole of gas in the reactant, so 0 minus 1 will give us -1. But basically what this describes is how does Q change as we affect pressure. So if we have a negative pressure dependence, it means that as we increase pressure, Q gets smaller, so the reaction will actually go forward to compensate. If we have a positive pressure dependence, it means that Q will get bigger as we increase pressure, so to reattain equilibrium, we'll actually go backwards to compensate. And this is going to dig more into Le Chatelier's principle. You're welcome. Other questions? Oh, yeah, ask all the questions you want. This is basically your office hours. So in terms of finding EA from an activation energy diagram, it's one of those things we're required to teach it, and it's weird that we teach it, but okay, we're going to teach it. So if you look at a typical reaction, we have our reactants, our products, and our activation barrier, our transition state, sits at the top of this hill. So our EA is the energy difference between the transition state and the reactants. Now, it isn't the energy of the transition state because when we do these calculations, that isn't necessarily 0. So if this is 80 and this is -20, the difference between these two is actually 100 kilojoules per mole. So to find the EA from a plot of activation energy versus reaction coordinate, it's just the energy of the transition state minus the energy of the reactant. Now, as far as preparing for the ethics lab, there's no preparation involved, and it's not required for your lab notebook. The ethics is more meant, we teach ethics at Wake Tech to combat basically what's happening right now in the scientific world in general is that there's just bigger and bigger issues of integrity. So what's going to happen with the ethics is that you're just going to click on the pre-lab assignment, read it, answer the questions, submit those, and then work on the post-lab assignment, which is a different case study, and answer the questions of those two case studies. But there's no prep, there's no reading ahead. This is very much a self-contained assignment. And if you've taken chemistry at Wake Tech, you've probably had one or two instructors who have taught. If you took chemistry 1 at Wake Tech, you may have had an instructor who also did the ethics assignments. It's going to be very similar to that. But the ethics is kind of low weight. Like, it's much more opinion, like what's your opinion and defending your opinion. But you don't need to like do any type of prep or pre-lab. Just answer the questions and work the case studies. Yeah, you're welcome. Please feel free to ask any questions you have. This is your time. Yes, so anything you're doing in WebAssign, you need to include in your post lab. That said, you don't need to like write everything down verbatim. So if you just want to do like, if you don't want to write a complete sentence, you can just get like a 1 or 2 word answer. That's just fine. But yeah, this is kind of meant to simulate what you would have been doing in the lab, where you would have transcribed your post lab into your lab notebook. Basically, your post lab now is the WebAssign, and you're just going to transcribe the WebAssign into it. Now, I will say you don't need to include the definitions. So if it like asks you what this is, leave the definitions, but definitely explanations like errors, those need to show up in there. You're very welcome. Well, we are already in week 5. Man, this has gone fast. All right, we gave y'all about another 4 minutes, and if no one's got any more questions, we'll head out for the day. Actually, while I do have y'all here, I did have someone ask me a question about the final, so I know I'll have to repeat this again anyway, but the final is July 13th, but it will actually open up July 10th, the Friday beforehand at like 12:01 in the morning. So for those of you looking towards the final and worried about what's going to be involved, you have that whole weekend plus Monday till 5 p.m. to take the final exam. It's a multiple choice final exam done online through Blackboard. It's hard because there's a lot of questions on it, but I would not say any questions are particularly like very in depth. So yeah, you're going to have a lot of time to take the final exam. So big thing I'm going to make sure you have by Friday, that July 10th, is all the grades posted. So you'll know your lab grade, you'll know your homework grades, you'll know your quiz grades, you'll have all that information, so you'll know what you need to get on the final in order to pass the course. So as far as the final goes, it's not that it says July 13th on the calendar. That's because that's when the official final would have been. But again, I'm going to give you the whole weekend to take it, so you're not rushing for time. And that will be the last thing you have to do, so it's not like you're going to have other things to turn in along with the final. When you go to take the final that Friday, that's it. That's the only assignment you have left in the course. Now, if you want to drop the course, don't take the final. If you take the final, you are completing the course. So once it becomes successful, and you say, well, I'll take the final so I can have the practice for the next time I take the course, I have to give you the grade in the course at that point. So if you think about dropping by that point, do not take the final. All right, if there's no other questions, I'm going to head out. Thank all of you who were able to show up today. And again, feel free to email me questions. You've still got the chat. Test starts this week, so make sure you go ahead and get that taken care of. And I will see you all tomorrow.